Okay, so I'm just going to go through a quick example about the approach to limit cycles. It's a slight deviation from problem 6 in the homework, so it may help you conceptualize that a bit better. Also, it's related to the next topic that we're going to cover, which focuses on the Mathieu equation. So the particular example is what's called the Rayleigh oscillator. And it's a nonlinear oscillator that has a standard oscillatory operator. And then the weak corrections come from friction here, as well as a nonlinear term that depends on the velocity of the operator. Okay. And we're going to take the case where the initial conditions are that the oscillator is at its equilibrium position, but has some initial velocity 2a. And we are going to determine the shape of limit cycles, okay, or the long-term oscillatory behavior of this equation to leading order. Okay. Of course, we're going to use multiple scales in order to do this. So to start with, we'll assume 2 time scales, t and tau equals epsilon t. Okay, we can always start with this assumption. If we suspect we need multiple time scales, you're free to make this an arbitrary order. And if you can't eliminate secular terms, for instance, you may need to take a different scaling in the long time scale limit. So that means that if we take sort of a standard scaling for our time scale, we might expect a standard power expansion for our solution. Okay. So at order 1, if we plug this in, you see here the right-hand side as epsilon. So the leading order behavior is just going to be a standard linear oscillator. Y0, 0 is going to start at 0, and dty0, 0, 0 is going to be 2a. This means that y0 is equal to some slowly varying amplitude times e to the it plus the conjugate of that, a bar of tau e to the minus it. And our initial conditions give us that a0 plus a bar of 0 is equal to 0, and ia0 minus a bar 0 equals 2a. Okay. Now, to order epsilon now, we're going to now involve some of these terms that arise through the epsilon terms on the right-hand side. We're going to have an dty0 term here, a dty0 cubed term here. But also remember, when we expand out these second order linear operators, right, recall that d dt squared is going to end up being dt squared plus 2 epsilon dt tau plus epsilon squared d tau squared, right? So we're going to now involve this acting on y0. So what we have is dt squared plus 1 of y1. That's our homogeneous part, minus 2 dt d tau y0 plus dt y0 minus a third dt y0 quantity cubed. So I can write this out as minus 2I a prime tau e to the it minus I a bar tau prime e to the minus it plus I a e to the it minus I a bar e to the minus it minus I a e to the it minus I a bar e to the minus it quantity cubed divided by 3. Okay. So from that, we're going to have to find all our secular terms and make sure that we zero them out. Okay. Now, if I rewrite this equation now, what I end up with is 2I a bar prime of tau e to the minus it minus a prime tau e to the it plus I a e to the it minus a bar e to the minus it minus 1/3 minus IA cubed e to the 3IT plus IA cubed, a bar cubed, e to the minus 3IT plus 3I a squared a e to the IT minus 3I a bar squared a squared magnitude squared e to the minus it. Okay. All right. Now what's important is really just setting the secular terms to 0. So we have a secular term there, secular term here, secular term here, 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 and here. So the 3it and minus 3it terms don't really matter. Okay, so if we set our secular terms to 0, what do we get? We get e, for the e to the it terms here, we got this one, and this one. I have 2I a prime t, tau, excuse me, IA minus I a squared a is equal to 0, plus 2I, so to the minus it, plus 2I a bar prime tau minus IA plus I a squared a bar is equal to 0. And if we set a of tau equal to r of tau e to the I theta of tau, where r and theta are both real functions, okay, then what we can do with, for instance, the first equation is write it as minus 2I r prime e to the I theta plus r e to the I theta prime plus I r e to the I theta minus I r cubed e to the I theta equals 0. Okay. Now we can separate these out, right, using, for instance, Euler's formula. And in that case, we end up with minus 2I r prime cosine theta plus I sine theta plus I theta prime r cosine theta plus I sine theta. Okay. Actually, in fact, we could be eliminating, think all of these terms, but yeah, you could also eliminate these EVI theta terms here. And that should work out to be the same, but let's just use Euler's formula and see how this comes out. Okay, so if we and now plus IR cosine theta plus I sine theta minus I R cubed cosine theta plus I sine theta. Okay. We end up with the real parts is going to be 2 sine theta r prime plus 2r cosine theta theta prime minus r sine theta plus r cubed sine theta equals 0. Our imaginary part then is going to be minus 2 cosine r prime plus 2r sine theta theta prime plus r cosine theta minus r cubed cosine theta equals 0. So if we take sine theta times the real part minus cosine theta times the imaginary part, then we end up with 2r prime minus r plus r cubed is equal to 0. In other words, 2 dr d tau is equal to r minus r cubed. And if we take cosine theta times the real part plus sine theta times the imaginary part, this is equal to 2r theta prime is equal to 0. So this implies that either d theta d tau equals 0 or that r equals 0, in which case we have a trivial proof. Okay? So let's just ignore that possibility for now. We can solve this equation using separation of variables. Okay. And we get that r tau is equal to r0 divided by the square root of e to the minus tau plus r squared of 0, 1 minus e to the minus tau. And we have that theta of tau is equal to just theta 0. Okay. So if we apply our initial conditions, those are that y00 is equal to r0 times e to the I theta 0 plus e to the minus I theta 0. That's equal to 0. This is going to imply then that theta 0 is equal to minus pi over 2. And since we could also take positive I pi over 2. And then we have dt y00 is equal to r0 times I e to the minus I pi over 2 minus e to the I pi over 2, which is equal to 2r0, which is equal to 2a. So that means that r of 0 is equal to a. So at the end of the day, what we have is y is approximately equal to 2a sine of t divided by the square roots of e to the minus epsilon t plus a squared 1 minus e to the minus e to the minus epsilon t. Okay. So that implies that y is approximately 2 sine of t as t goes to infinity. Okay. So what we have then in general is that for a greater than 1, that over time that our oscillation is going to settle down to this amplitude, okay, which is going to be 1 here. when A is less than 1, we're going to have it build up to this amplitude over time, exponentially relax to it. Okay? And so if we were to draw this in the phase plane, so here's y prime and y, then we should expect there's some limit cycle here, and we'll get a spiraling into it over time, or spiraling out to it over time. Okay? And so the limit cycle is going to behave as an attractor. Okay? That is going to be drawn, that's going to draw solutions to it asymptotically over time. Okay? And what we've done by looking at this slow time scale dynamics is we've extracted the slow time scale behavior of this amplitude that's going to modulate how high and low this oscillator goes over time. Okay, that's a Rayleigh oscillator. You have a similar problem on your homework that some of you already worked out, maybe, but hopefully this will be a helpful guide for that. Okay, that's it for now. See you on Wednesday.